In this video, we will begin our investigation of the natural logarithm function. Specifically, we will provide a definition from a calculus perspective and determine what its derivative is so that we can work through a few examples. So let me note the natural logarithmic function is defined as follows. We say that the natural log of x is equal to this integral from 1 to x of 1 over t dt, where x could be any positive value you would like. Now this most likely looks very different than how you have thought about the natural logarithm in the past, but I assure you this is the same natural log function that you've encountered in, say, pre-calculus or algebra courses. So just to give a little intuition, if we were to include a graph, 1 over t would be something that looks kind of like this. If we consider positive values, and we are integrating from 1 to x. So natural log of x, and in the picture here I've drawn x to be bigger than 1, you have this region enclosed underneath the curve, and I'll say it has area A. The natural log of x is equal to that value of A. If x was a value which was less than 1, the natural log would end up being a negative quantity. Now, from a calculus perspective, at least in this initial video, the most important thing for us is what is the differentiation formula associated with the natural log, and then can we just practice a few examples. So recall from the fundamental theorem of calculus, the first part, if we have a definite integral from a to x, f of t dt, differentiating this can be the easiest derivative we ever evaluate. You take that x, which is our upper limit of integration, you plug it in for t. So looking at how the natural log is defined, if we want it to differentiate, we would take this x, plug it in for t. So with this in mind, the derivative of the natural log of x by the fundamental theorem of calculus is simply 1 over x. So let's use this formula to evaluate several derivatives. So common examples are just going to involve somehow combining the natural log with other functions, where we use the chain rule, quotient rule, product rule. So looking at the first example, if we want to differentiate natural log of sine of x, we see we have a composition. You have this inside function sine and the outside function natural log. So the chain rule tells us the following, that we would take the derivative of the outside function and the derivative of natural log, let me remind us, is 1 over x. So derivative of the outside evaluated at the inside multiplied by the derivative of the inside. The derivative of sine is cosine, so this becomes cosine over sine. And you could certainly leave your answer in this form, but just note from a trigonometric definition, cosine over sine is really cotangent. Similar in this second example, we see we have a composition. We have natural log as our inside function, square root as our outside function. So if we want to differentiate this using the chain rule tells us we take the derivative of the outside function, so that would be 1 over 2 square roots. We evaluate this at the inside function, and then we multiply it by the derivative of the inside function. And the derivative of natural log of x is, of course, 1 over x. So we have 1 over 2 square roots of natural log x multiplied by x. So at this point, we can really think of just having a new differentiation formula associated with the natural log. Once again, the reminder, the derivative of the natural log of x is 1 over x. So for the last derivative, to differentiate x squared times natural log sine x. The first thing we might notice is that we have a function, x squared, times a second function, natural log sine. So we'll need to use the product rule. So we'll simply write out what the product rule tells us. we take the derivative of the first times the second plus the first times the derivative of the second. And once we've written out the product rule, it really just boils down to evaluating these two, hopefully easier to handle derivatives. By the power rule, the derivative of x squared is 2x. And if we go back to the previous slide, the first example, we actually already differentiated the natural log of sine of x, and we found that it was cotangent x. And no reason to recreate the wheel, so we'll just simply copy down the formula we had from a previous slide.